Chemical Equilibrium Part 9, the Chateliers Principle and Pressure Volume Changes. Okay, so let's remind ourselves about stressing a chemical system. And remember that chemical reactions that are at equilibrium already like to stay at equilibrium. So if we do anything to disrupt that equilibrium state, then it's considered a stress. Now, last time we talked about some of the different kinds of stresses, and in the previous presentation we talked about what happened, which way the equilibrium shifted when we added or removed product or reactant. Now we're going to talk about gaseous systems where we change the pressure on a system or we change that volume of the system. Just reminding ourselves, when we have a chemical reaction at equilibrium and we stress it, the equilibrium point is going to shift in the direction that counteracts the stress applied. So what does that mean in terms of pressure and volume changes? So let's talk about this with examples, because it's a little bit easier to understand that way. So here's the same reaction that we've been looking at, nitrogen dioxide in equilibrium with dinitrogen tetroxide. And now we're going to increase the pressure on the system. And so we want to think about what happens to the volume of that system. So remember, the ideal gas law, PV equals nRT. Now if we hold the temperature constant, these two are constants, moles of gas and the gas constant. So we have P times V is equal to a constant. Now if we increase the pressure, so we make this number bigger, then what has to happen to this number? And so when we increase the pressure, then the volume has to go down. So what we want to think about is, does the equilibrium shift? And if it does, which way does it shift? Now when we reduce the volume of a system, and we do that by increasing the external pressure, then the equilibrium is going to shift in the direction of the smaller number of moles of gas. Now why would it do that? So we're going to go, in this case, we reduce the volume, the equilibrium is going to shift toward dinitrogen tetroxide. So why? Well, basically it's trying to reduce the pressure. Each individual gas molecule bumping against the walls of the container is going to create that pressure. If the system can reduce the number of hits by dimerizing, by sticking two of these guys together to only have one, then it can reduce the pressure inside the container. And so it's trying to undo what we did. We decreased the volume by increasing the external pressure. The chemical system is going to try to reduce that pressure. Now, what happens when we add a non-reactant or product gas, and we call those inert gases, to the reaction flask at constant volume? All right, so what we're going to do is we're going to add more gas, but it's going to be nitrogen, so it's not going to be something that's reacting. And we're going to keep the volume constant. So think about adding gas to a rigid container. What's going to happen to the pressure inside that container, and will the equilibrium shift? So if we add this inert gas at constant volume and temperature, the equilibrium does not shift. Now why is that? That seems kind of strange. And even though the total pressure inside the flask has increased because we added nitrogen gas, so we added a partial pressure of nitrogen gas, so this total pressure increased, but the reacting gases, those partial pressures stayed the same. And so this is just a reminder of Dalton's law of partial pressures. So each gas in the container doesn't know the others exist. So nitrogen dioxide has its own partial pressure, dinitrogen tetroxide has its own partial pressure, and because we've added a reacting gas and we didn't allow the volume to change, then the reacting gases don't care that this guy is around. So all that did was increase the total pressure, but the partial pressure of each of our reacting gases stayed the same. Now, let's compare this, because now we're going to get a different result. If we add the same inert gas at constant pressure and temperature, then what's going to happen, and will the equilibrium shift? And so as kind of a spoiler, the equilibrium is going to shift in this case. So we're going to think through this. Okay, so as we add this gas at constant pressure and temperature, so we're going to keep P the same, okay, but we're adding gas, total pressure stays the same, then what has to be happening to the volume? The volume has to be expanding to accommodate that gas. Okay, so if we keep the total pressure constant, then we must be increasing the volume. So it's kind of a sneaky way to increase the volume on a system. And if the volume increases, then the partial pressure of each of the gases in the container is going to go down. So using the same expression that we used earlier, we're increasing the volume in order to remain at a constant value here. We're increasing the volume, so the pressure, the partial pressure of each gas has to go down. So as the volume expands, the partial pressure of each gas goes down. So now what happens? Well, when the partial pressure of each reacting gas goes down, the equilibrium is going to try to make up for that. And so it's going to shift in the direction of the larger number of moles of gas. So now the system is trying to replace that lost gas pressure. So we've reduced the pressure, those partial pressures, and now it wants to replace it. It wants to counteract what we did. So now the system is going to shift in the direction of the larger number of moles of gas, so it's going to shift toward nitrogen dioxide. As this equilibrium shifts in the direction of the larger number of moles of gas, it's going to go toward reactants, which is basically 2 moles of gas versus 1 mole of gas. So here's a mini quiz. Here's a reaction. 4A, this is a gaseous reaction. 4A goes to B, which is a gas, and C, which is a solid. And so we are going to reduce the volume at constant temperature. So which direction does the equilibrium shift? So pause this and give that a try. Okay, so the equilibrium is going to shift in the direction of the smaller number of moles of gas. So we have 4 moles of gas on the reactant side, 1 mole of gas, so you have to pay attention to these phase labels, 1 mole of gas on the product side, and so the equilibrium is going to shift toward the products, the smaller number of moles of gas. And it's going to try to reduce that pressure inside the container when we reduced the volume. Okay, next up, we're going to talk about Le Chatelier's principle and temperature changes.